Good day or good evening. This presentation is on thermosphere model assessment under geomagnetic storm conditions. I give this talk on behalf of Claude Boniface and myself, Ssean Bruinsma. Hi. So far, thermosphere model assessment under storm conditions was mainly done for specific storms or a couple of storms, or let's say all storms with the same satellite. Now we present density data of 13 storms and updated metrics for comprehensive and standardized thermosphere model assessment under storm conditions. All assessments are done for semi-empirical models, NRL-EMSIS, JB08, and DTM 2013, as well as two first principles models, TIE-GCM and CTIPI. Part of this work was done in the framework of the International Space Weather Action Team Cluster G2A, Atmosphere Variability. So this initiative started about 1 or 2 years ago, and here at the bottom you see a screenshot of the website. So the new metrics and procedure for a storm assessment are as follows. So we cut up a storm event into 4 phases: a pre-storm phase, an onset phase, a recovery phase, and a post-storm phase. The pre-storm phase, phase 1, so this period just before the storm is used to debias the model densities. So they are scaled, centered on the observed densities. Then density ratios, so mean and standard deviation, are calculated for each of the 4 phases as well as for the entire event, so phase 1 to 4. All these phases are centered with respect to T0, which is the minimum of the DST. Secondly, we compute amplitude and phase, so the timing of the max of the peak, as follows. So we have a model peak here in orange and an observed peak in blue, and this relative amplitude is the error. Secondly, we have a delay or advance of the model peak, and this is also determined. So here are the 13 storms that were used in the assessment using Champ, Grace, and Gautier densities. So you can see the Gautier storm profiles, bottom left, and you can see there are only 3, and the blue one, the blue curve, is not even complete for the full interval. So that is one of the main problems we have with the storm time assessment, is that our database is rather sparse. So here are the results. First, for the mean density ratios. And these are calculated, like I said before, for each of the 4 phases. So these are the black numbers. And for all 4 phases, these are the red numbers. And it's computed for NRL-EMSIS, DTM, TIE-GCM-H, which is TIE-GCM with the Helix driver, TIE-GCM-W with the Weimar model as a driver, CTIPI, and JB08. Mu is the mean per phase. Let's just concentrate for the moment on the total storm event. Excuse me. So you can see here that for this parameter in the metric, DTM 2013 and TIE-GCM Weimar give the best results. So they have a mean density ratio which is almost 1 with a very small scatter. The scatter here, the sigma, is the scatter of each time of all the storms in the phase. Secondly, what you can see, for example, for NRL-EMSIS is that during the storms, onset and recovery, there is significant underestimation. For TIE-GCM with Helix, you can see that first we have an underestimation followed by an overestimation during the storm. And this particular error is well repaired when you switch to the Weimar model as a driver, you can see here that this is much, much improved, and it even leads to the best results for the total storm. So this is the same sequence of plots, so the models and the phases and the total results, but this time for the standard deviation per phase and for the total, so expressed as a percentage. In this case also, on average, the lowest standard deviations are obtained with DTM 2013 and TI-GCMW. Another thing that is expected is that we see that the standard deviation are lowest for green, which is GOES, which is the lowest altitude satellite, and highest for GRACE, the blue, which is the highest altitude. And you see this, of course, in all models. The final result, so we have the relative amplitude error and the delay at the bottom. Here, the results are a little bit different. So you see that here, the smallest mean error in amplitude is obtained with JB08, as well as the best timing of the peak, 0.07 hours on average off, but with large spread. And in this case, JB08 is underestimating by 21% on average. And the best first principles models in this case is CTIPI with a 20.6 overestimation and a delay of about 0.37 hours off. So the take-home message, the Thermosphere model assessment was done for 13 selected storms, and these storms were isolated events. With that I mean they had a nice single clear peak, and this was done according to a tailored and unambiguous procedure, which is a compromise, typically because we chose the fixed length intervals for the phases 1 to 4, for example, but this was done taking into account that we want this procedure to be easily automated. So the assessment of the models was done, and we have seen that the storm onset phase 2 is always least accurately modeled, even if the recovery phase, so phase 3, is only slightly more accurate. The overall performance, so phases 1 to 4, is best with DTM 2013 and TI-GCMW. The peak amplitude and phase are best reproduced with JB08 and CTIPI for the first principles models. NRLMSys significantly underestimates the storm amplitude, 60% on average, and this actually confirms earlier studies. Finally, using the Weimar instead of the Helix model in TI-GCM leads to significantly more accurate storm modeling, and this model should, if possible, always be used when running TI-GCM. Thank you.